Welcome to lesson 96, our introduction to quadratic equations. At this point in our algebra course, we've studied all different types of functions, linear functions, exponential functions. We're going to get into what are called quadratic functions. A quadratic function is any function that can be placed into the y equals ax squared plus bx plus c form, which it says right here. Really important, it says that a cannot be equal to 0. A is always going to be our leading coefficient. It's our number in front of our x squared. B and C technically can be zeros. Sometimes they are, sometimes they are not. But A, the number in front of x squared, cannot be 0. Now, based on that definition, we're going to answer a couple of little questions before we really get into quadratics. The first one is, why is it important for the leading coefficient to be non-zero? If you take a look at what a quadratic is, it's y equals ax squared plus bx plus c. If for some reason you had that a was equal to 0, that means that you would have 0 times x squared plus bx plus c. And we should know that if we simplified that, x squared times 0 is going to be 0, that it would no longer be a second degree polynomial function. The exponent of 2 would go away, and what we'd be left with would be linear. The second point we need to make sure that we're clear on is that when we are graphing, or looking at a quadratic function rather, it's important for us to write it in standard form and be able to identify that leading coefficient. A couple reasons for this as we get into our lesson. First thing I'm going to do is put it in standard form, which we've talked about before. Standard form means our exponent should go from greatest to smallest. So I'm going to rewrite it as y equals negative 3x squared. Then I'm going to go plus 7x, and then I'm going to go a plus 10. Once we have it in standard form, to identify our leading coefficient will be the number in front of our x squared. So in this case, our leading coefficient would be negative 3. That value of negative 3 is going to have some significance, especially when we look at the graphs of quadratics. It's going to influence the direction that it opens, whether it opens up or opens down. And we'll see that as we get into our graphing part of this unit. Last thing we're going to take a look at, it says if f of x is equal to 2x squared minus 3x plus 1, without using your calculator, find an f of negative 2. Now, this is really just making a connection to something we've already done. We've talked about evaluating functions, taking a number and plugging it in for x, and that's really all this is. If I have f of negative 2, I'm going to take negative 2 and put it in for x. So it's going to be 2 times negative 2 squared minus 3 times negative 2, and then plus 1. Now, what I'm going to do is just carefully do the arithmetic for this. If I take negative 2 and I square it, I get 4. So that's 2 times 4. If I take negative 3 and negative 2, multiply them together, I get a positive 6, and then I have a plus 1. 2 times 4 is 8. 8 plus 6 plus 1 gives me 15. Now, the connection we're looking to make here is that when we evaluate a function at a particular number, the number we put in, our input, is part of our domain, and our output is part of our range. That's just another way of saying that we have an x value of negative 2 and a y value of 15. And if we were to take a look at the graph of this quadratic, you'd see exactly that. You'd see that there'd be a point at negative 2 comma 15. All right, so now that we've talked a little bit about what it means to be a quadratic in terms of it being an x squared, a second degree polynomial function, we're going to talk about what the graphs are going to look like. And it's important for us to understand that quadratics are really just a type of functions. Just like any other functions, our inputs are going to go in, our outputs are going to come out. We're going to notice that there are some differences between quadratics and the linear functions and exponential functions we've seen before. The most notable difference is that the outputs are going to repeat, not for all quadratics, but for a lot of them. Now, the second example we have here says that we're going to take a look at the function f of x is equal to x squared. We're going to take a look at the inputs, take a look at some outputs, take a look at the graph, describe what it does, talk a little bit about its range. First thing we're going to do is fill in our table. Like with any other function, we're going to take an x value, plug it in, and we're going to get back a y value. So to fill in the first box on my table, I'm going to take negative 3 and I'm going to square it. Negative 3 times negative 3, of course, gives me a positive 9. Then I work my way across my table. Negative 2 times negative 2 gives me a positive 4. Negative 1 times negative 1 gives me a positive 1. 0 times 0 gives me a 0. 1 times 1 is 1. 2 times 2 is 4. And then 3 times 3 is 9. I mentioned as we started this that one of the things we're going to notice is repeated outputs. And if you take a good look at our table, you're going to notice that we're going to have a 9 that came up twice, a 4 that came up twice, 1 came up twice, and then we're going to have one unique value that's going to be in the middle of our table, and this is going to happen more often than not, and that middle value is going to be important to us. Now it says here we're going to graph it, so I'm going to take each of those x's and y's and graph them. So I'm going to point at negative 3 comma positive 9, so starting at the origin, count 3 spaces to the left, and then 9 spaces up. Then I'm going to have another point at negative 2 comma positive 4, and then negative 1 comma positive 1, point at 0 comma 0, point at 1 comma 1, 2 comma 4, and then 3 comma 9. Now, once we've plotted our points, one of the things we're going to notice is that we're not going to graph it using a ruler. We're going to make a nice smooth curve. So I'm going to connect these points as neatly as I can with a nice smooth curve. I'm going to put an arrow on both sides indicating that it does go farther than that. And then I'm going to label my graph as f of x is equal to x squared. Now, the general shape of a parabola is, or a quadratic rather, is going to be what we see here, and it is called a parabola. The next question we have is to identify the range. Now, range is a term we talked about when we talked about functions. Range is really just our outputs. If you think about it, range, we're looking for highs and we're looking for lows. Now, based on the graph that we have here, I would say that the lowest point that I have in my graph is going to be this point right here, and that every y value is going to be from that point up, because looking at the curve, it's from that point up. So I would describe my range as being my y values, and those are going to have to be greater than or equal to 0. Now, please remember, we've done this in interval notation as well. In interval notation, it would be from 0 to positive infinity. I would include the 0 with a bracket, and the infinity would get parentheses. Now, it's important for us to note quadratic functions can obviously become more complicated than our last example, but strangely enough, they're all going to be the same general shape. That general shape, as I mentioned before, is what's called a parabola. That U shape that we have in this graph is described as a parabola, and that's going to be pretty consistent throughout most of our quadratics. As we look at our next example, it says that we're going to graph the quadratic y equals x squared minus 2x minus 8. Now, I said just a moment ago that sometimes these quadratics will become a little more complicated. They're always going to be that general shape of a parabola, but we're going to have a little more work to figure out our values. It says in this question that we're going to use our calculator to generate a table. Using your graphing calculator and y equals, you can plug in your equation, and it'll give you back the table that goes along with it. You're going to notice that I've already done that, so if you take a look at what I have, I've already entered into y1, x squared minus 2x minus 8. To get the table that I'm going to fill in, I'm going to press the second key in the graph button, and it's going to pull up the table that I have here. Now, you're going to notice that there are some similarities between the numbers. If you take a good look, there's a 16 at the top and a 16 at the bottom, and then there's a 7 and there's a 7, there's a 0 and a 0, a -5 and a -5, -8, -8, and then there's that unique one, which is -9. So I'm going to start my table with that point that's in the middle, that 1, -9, and I'm going to build it from there. Now, the middle of my table would be right here, and again, that was at 1, that -9 was my y value. And then I'm going to go back to my table, and I'm just going to build it out. And I normally start with that point that's in the middle, and I'll include 3 points that are above it, and I'll include 3 points that are below it, depending on the directions for my question. So it looks like my x's will go from -2 up to +4. So I'll go back to my table. I'll go -2, -1, 0, 1, 2, 3, and then 4. If I go back to my graphing calculator and look at my numbers, my y values are going to go 0, -5, -8. So I'll go back to my table. I'll put in a 0, a -5, a -8. Then I have that -9, which was the one that was in the middle, and then they really just repeat because of the parabola itself. So it's a -8, a -5, and then it's a 0. So first thing we did was use our calculator, plug the equation in, get the values for our table. Now I'm going to go ahead once again and state the range. Now, I haven't graphed my function yet, but if you think about it, your range is going to be your y values, so you should be able to look at your table and get a general idea of what those are. But based on our picture, we should be able to get a better idea. So I'm going to point at -2, 0. I have another point at -1, -5. 1, 2, 3, 4, 5 down. 0, -8. 1, -9. And then, because it's a parabola, it just sort of repeats itself as I work my way out to the right-hand side. I'm going to go one space to the right, and then I'll have points that are in the same basic places. Same thing as I did before. I'm going to go ahead and connect it with a nice smooth curve. I wasn't told specifically what y values to use, so I'm going to again extend it with an arrow in both directions. You'll see as we do more of these questions, sometimes we'll do that, sometimes we won't. It'll really depend on the information that we're given. All right, so now that I have a picture to look at, I'm going to try and identify the range. Now, just like before, ranges are tops and bottoms, is my y values. The point that I have there in blue, that's the bottom of the parabola. Well, the bottom of the parabola is located at a y value of -9. So if you look at your graph, every point on the curve is going to have a y value that's greater than or equal to -9. So I would say that my y values would have to be greater than or equal to 9. And as I said, in interval notation, that would be -9 to positive infinity. It includes that -9, and it just goes up forever. Question letter C says, over what domain is the function increasing? Well, we should remember this from previous units. To be increasing means if I look at it from left to right, it's going up. So if you think about it, If I were to start at this point that I have in blue and I were to trace the curve as I go to the right of that point, that entire graph is going up. So that would be my interval of increase. Interval of increase would start at the x value that I have here, which would be at -1. So I would say the interval of increase would start at x is equal to -1. So it would have to be any x value that's greater than 1. And again, if we wanted to put it in interval notation, it would be from 1 to infinity, meaning to the right of 1, not really including that 1. Now the next thing we'll talk about are a few terms that are important for us to know. To state the coordinate of the parabola's turning point, also known as the vertex. These two terms, turning point and vertex, are going to be sort of interchanged. Some questions will refer to the turning point, some will refer to the vertex. And it's really just this point that I highlighted at the bottom of my graph. Sometimes it'll be a minimum point, meaning the lowest point on the graph. Sometimes it'll be a maximum point, meaning the highest point on the graph. In this case, the turning point is going to be located at +1, -9. It's, again, the lowest point on that graph. You can also identify the turning point from most of the tables that go with parabolas. It would be that point that's in the middle that's unique, the one that I kind of used as my starting point for this particular table, would give me the coordinates of the turning point. The next term that it mentions is the axis of symmetry. Now, the term symmetry we should be familiar with. It really just means that we can divide it in half to create a line of symmetry. So the axis of symmetry is going to be a line that's going to go straight up and down through that turning point or through that vertex. So this would be my line, that would be my axis of symmetry. If you think about it, I can now fold the parabola in half on that line, really just balancing. For a parabola that opens this way, it's always going to be that line that goes straight up and down through the turning point, and the equation for the axis of symmetry is going to be x is equal to. And since this line travels through +1 on the x-axis, it's going to be a line whose equation is x is equal to +1. Next thing we're asked to find, it says, what are the x-intercepts of this function? These are also known as the function's zeros. You're going to see as we get more into parabolas that sometimes it'll be x-intercepts, sometimes they're referred to as zeros. I've also seen them referred to as roots. So x-intercepts, zeros, roots, they all mean essentially the same thing, where the graph hits the x-axis. So what I would do is I would go back to my graph and I would just simply identify where the graph hits the x-axis. Well, the graph hits the x-axis obviously here and there. So those are my zeros, those are my x-intercepts. And if you look at your table, you can identify them as well by finding y values that are equal to 0. So I would say -2, 0, and 4, 0 would be the roots, would be the zeros, would be the x-intercepts. So again, that would be -2, 0, and +4, 0. So some terminology that's important. We should know turning point and vertex are interchangeable, really mean the same thing, either going to be the highest point or the lowest point. In this case, it's the point 1, -9, and as I mentioned, that would be a minimum point. It's the lowest point of the graph. If the parabola were facing a different direction, if it were the highest point of the graph, we'd call it a maximum. Now, the last question we're going to take a look at, it says the quadratic function f of x has been selected with selected values shown below. What are the coordinates of the turning point? Now, I mentioned this to you before as we looked at the table, we looked at the graph. Now, this information is exactly the same as what we've talked about. We just don't have a picture to work with. If you look at your table, you're going to notice that there are numbers that are repeating. So that +4 and that +4, that +9 and that +9, +12 and +12. But then you're going to notice that there is a point that does not have a repeated y, has a unique y, and that would be the point 2, 13. And if we're given a table like this, the easiest way to identify that turning point would be to find the one that does not have a repeating y. Now, if you look at the range, based purely on this table, if I'm talking about a range, I'm looking for a low and I'm looking for a high. If I look for the lowest y value, the lowest y value would be -2. If I'm looking for the highest y value is going to be that 13. So based on this table and just this information, the range would be from the lowest value, which would be that -2, and that would be less than or equal to my y value, which would be less than or equal to the highest y, which was 13. Again, we can put this in interval notation. Interval notation, it would be -2, 13, and it's inclusive. It would include both of those terms. So that's going to conclude our introductory lesson to quadratics. Again, it's y equals ax squared plus bx plus c. That's the basic form of a quadratic equation. A, the number in front of x squared, cannot be 0. Terms that we've talked about that we need to make sure we know would be vertex, turning point, axis of symmetry, range. There's going to be a lot of connections between what we've done with other functions and what we're going to do with quadratic functions.